My name is Seok, and today I'm going to present about the early phase field planning using the digital twin and environmental factors. And this project is sponsored by BP. Well, the main purpose of the field development is to maximize the value of the field. And there are many different field development solutions simply because every field has different characteristics. And this is the fundamental reasons why we do have always the fit for purpose field development solutions, as you can see in the figures. To find the single optimal field development solution in the end, several other field development solutions concepts are evaluated during the early phase field development process. And these field development concepts are ranked by the value. And the final solution that is expected to yield the maximum value will be selected after all the evaluation process. But to increase the value of the field, then the early phase field development planning is the key, because this is the design stage where the most critical design features are determined. And also once it is determined, it is very hard to make changes in the later stages. So therefore, it is not an exaggeration to say that the success or failure of the entire project depends on early design phase, as the final project value is influenced significantly, as you can see in the figures. Well, since we care about the value of the field, then let's talk a little bit more about the meaning of the value. Here, when it comes to the value of the field, usually it indicates the economic value in most cases in upstream industry. But in these days, the meaning of the value has been changed due to the climate changes, as we all know. So nowadays, the value of the field does not only mean the economic values, but also means the other values like low greenhouse gas emissions and the field energy efficiencies. But we have observed that the current field design procedures tend to consider only economic values, neither greenhouse gas emissions or energy efficiencies, which are becoming more and more important. Even we have the field development concepts which lowers the greenhouse gas emissions or increase the energy efficiencies, we must be able to evaluate those concepts correctly during the early design phase to find an optimal field development concepts. So, and this was the starting point of my research project, actually. So the objective of my research is to improve the current early phase field development planning method by considering not only economic values, but also the greenhouse gas emissions and energy efficiencies. And these are the points that I want to address today. And maybe you can briefly answer kind of like these questions at the end of my presentation, maybe. So the first one is, what is the main source of the greenhouse gas emissions in the offshore field? And the second one is how to quantify those greenhouse gas emissions and energy efficiency during the early phase field planning. And the last one is how to reflect all these values into the field development decision-making process. Well, let me briefly give you a background on about this then. So, in offshore field, there are several greenhouse gas emission sources, and among them, the gas turbine has been reported as the largest greenhouse gas emission source when generating power for the production operations. The gas turbine itself accounts for approximately 85% of the total greenhouse gas emissions at the offshore field in Norway. So we can say that a significant greenhouse gas emission reduction can be expected only by changing the gas turbines to the other method, like electrification, or we use more energy efficient gas turbines. So electrification means that all offshore installations are powered by electricity, not by the gas turbines. And currently there are two proposed concepts for the electrification. One, the offshore wind farm can be one option to power the offshore installation using the renewable energy source. And the other one is a power from shore, which can be another option for powering offshore installation by connecting national grid via subsea power cables. Increasing energy efficiency of the gas turbine can be another option to reduce the greenhouse gas emissions. Like combined cycle gas turbine can be a good example. The main principle of the combined cycle gas turbine is to use the waste heat from the combustion process to generate the additional power, electricity power. So in this way, the energy efficiency can be improved approximately from 35% to over 50%. To compare this with the open cycle gas turbine, which is normally used in these days, the combined cycle gas turbine uses less fuel to generate the same amount of power, meaning that less greenhouse gas emissions to the air. Then how can we include these options or these power supply methods in the early phase field development evaluation process? Then let's take a look at a real user case provided by Aker BP. Well, suppose that there is an offshore oil field that we want to develop. And the water depth of the field is very deep as 1,200 meters. And the existing infrastructures are very far located. And even there are no oil transportation infrastructures. And then the basic concept will become like this. Well, because of the water depth, the floating vessel with the subsea development can be a possible option for the field development. And we consider shuttle tanker for the oil transportation due to the lack of the infrastructures nearby. And since it is known as a tight reservoir, we can also think of the gas injection to support the reservoir pressure. And we can also consider multilateral drillings to increase the productivities of the wells, and we can also reduce the cost because of that. Then the subsea field architecture can be designed depending on the number of the producers and injectors. And on top of the floating vessels, basically we consider three types of these surface process, which including crude oil stabilization with some separation trains and gas compression trains for producer gas in reinjection and producer water treatment, which will include a lot of pumps in there. So here the surface process is very important because the power demand of the entire field is determined based on the surface process, or if we have the subsea process, that will also impact on the power consumption of the field. And those processes may have some heaters and several numbers of compressors and pumps maybe. So based on this, we can now move on to the power supply method. So here are four different types of the power supply options that I mentioned before. And to evaluate this, to evaluate field development alternatives, including this in the design phase, we can now make a value chain model, including every field development options mentioned before in this case study, which is one of the main contribution part of my research. So here is a schematics of how value chain model is created. It starts from the reservoir and well, and then integrated into the subsea production network model. Then the subsea production network model is combined with the surface process model to see the field production performance, like production and injection profiles, and so on. And this becomes the basis of the economic calculation, like NPV or break-even oil prices. But if we consider the greenhouse gas emissions and the energy efficiencies, then this is not actually sufficient. So one way to estimate the greenhouse gas emission and energy efficiencies is to include those power supply options into the value chain model. For the gas turbine options, we can include gas turbine model into the value chain model. And for the power from shore and offshore wind farm options, we can consider the capital expenditure of each options in the economic calculations, depending on the power demand. So first, we estimate the field power demand from the integrated production model from here. And then the field power demand is taken as an input to the gas turbine here, such that we can estimate the amount of greenhouse gas emissions and the energy efficiency of the field. We can then calculate the KPIs like emission intensity or energy intensity of the field, which will later support the decision-making process. In the economic calculation, we also consider the CO2 tax to investigate the influence of each power supply options on the field development. And each models were built by using different kinds of simulation softwares like Petroleum Experts, IPM, and Aspen HYSYS, and the final economic calculation is done by Excel. And here are the field production performance results from the value chain model for this specific case study. The field production of this specific field will peak at 4th year after all drilling operations. And by produced gas reinjection, the reservoir pressure does not show dramatic decrease, as you can see here, leading to increased cumulative production, like here. And as more produced gas is recycled and injected, the more energy needs for the compression of the gas at the surface process. So we can see the energy demand profiles here during the life of the field, and this will maintain the energy demand at a very high level if we compare to those 25% gas recycled cases compared to these cases. And here is a field economic performances, and it shows that the field development solution with the gas turbines are more profitable than the power from shore or offshore wind farms in this specific field case studies. And the difference between the open cycle and combined cycle, like this little difference here, it seems like it is negligible due to the trade-off between the higher CO2 tax for the open cycle gas turbines and higher installation and operation costs for the combined cycle gas turbines. And when it comes to the break-even price, oil price, the price is more dependent on the field production strategies and the amount of recycled gas than the type of the power supply method, actually. When looking at the field environmental performances, only field development concepts with the gas turbines are studied because power from shore and the offshore wind farm does not produce the CO2 when generating the power. So in the left figure, it shows the CO2 emission intensity as a KPI, indicating the amount of CO2 emission per produced barrel oil equivalent. For this field, the indicator shows that the amount of CO2 emission does not much dependent on the production strategy, but rather the types of the gas turbines. In general, the combined cycle gas turbine emits 34% less CO2 per produced barrel oil equivalent in these cases. On the other hand, when it comes to the energy intensity here, the red curve, the 75% of gas recycling case shows the largest energy intensity, followed by the 100% cases. So this can be interpreted that more energy is required to produce the same amount of oil than in other production strategies. So maybe field planners can consider some amount of gas injection when making decisions for better field energy efficiency, not injecting the 75% or like 100%, or maybe we can inject a little bit less than that so that we can emit less, we use less energies for the produced oil. Yeah. So in the right side figure, the break-even CO2 tax is shown. The break-even CO2 tax means the required CO2 tax for the field development concept conversion from the gas turbine to the power from shore or to the offshore wind farm. And this indicates that for this specific case study, the power from shore solution is the most viable in the near future. Like if the CO2 tax is increased from here to here, and while the offshore wind farm remains infeasible. It also illustrates that the gaps between the current CO2 tax with break-even CO2 tax required is yet too large. And finally, if we look at the total amount of CO2 during the life of the field, as we said, like 34% of reduction of total CO2 emission can be achieved by converting, by using the combined cycle gas turbines. And furthermore, if we electrify the field, we can have long-term CO2 emission saving effect compared to those cases using a gas turbines by around 1.8 to 2.7 megaton CO2 during the life of the field. So back to the presentation point. First, we have looked through the major sources of the greenhouse gas emissions. As I told you, the gas turbine is a major culprit of the greenhouse gas emissions in the offshore field. And current suggested alternatives may be power from shore, and offshore wind farm can be good alternatives if the CO2 tax is increased, or if we get probably more support from the government maybe. And also, secondly, we look through the method that how to quantify the greenhouse gas emissions and energy efficiency of the offshore field by building value chain model encompassing all the components from the reservoir to the top side, the surface process. And by using this model, we are able to examine different production scenarios as well and see its influences on greenhouse gas emissions and energy efficiency of the field. And lastly, we saw how these factors are reflected into the decision-making process. We use the KPIs like CO2 emission intensity and energy intensity for the field development decision support. And we can also estimate what is break-even CO2 tax for the concept conversion and effect of the present and the future CO2 tax by the sensitivity analysis together with the oil price. Well, I think the potential impact for this research can be like it can also be extended for. It can be also utilized for the other greenhouse gas emissions such as methane and nitrogen oxides, etc. And it can also be extended for new production systems, including CCS or other types of the energy storage options like batteries or hydrogen-driven turbines in the future, maybe. And furthermore, I think it is the method that I use using the integrated value chain modeling approach. It provides a relatively more reliable estimation if we compare it to the method using the emission vectors, because those emission vectors, it is known as quite uncertain and for using to use for the detailed evaluation. So yeah, that's it, and thank you for listening, and thank you for the Aker BP for the sponsorship, and yeah, please, yeah.